Hello folks, I'm happy to welcome you to our second video about the NEOROAST technology. And today we want to explore the question how this roasting technology differs from traditional roasting. I invited Dr. Stefan Stanowski, head of our Technics Center, to join this discussion.
Hello together.
Stefan, you have been for more than 15 years already with the Karl Group in development and research, so I think we will discuss some exciting information today.
I hope so, yeah.
Yeah, nice. Good. And in the background we see the NEOROAST with the RFB hot air technology, but today we focus less on the roasting technology itself, as I gave an insight already in the first video. Today we focus on sensitive topics. So yeah, I think we can leave the roastery and continue our discussion in our cupping room.
Okay, come on.
Yeah, so for smaller roasteries, the dominant roasting technology is still the traditional one, it's the drum roasting. But we are experiencing the increasing interest in hot air roasting for our clients in direct conversations or on trade fairs. So would you please briefly explain the differences between hot air roasting and drum roasting?
Yeah, sure. So in drum roasting, the coffee beans are heated up indirect by touching the hot surface. So scientifically speaking, this is heat transfer by conduction. So due to the high thermal inertia of the drum itself has to be heated up before it can transfer the heat to the beans. This gives us lower flexibility in creating roasting profiles we would like to achieve, or at least we would like to try out. Hot air, so direct heat transfer, again scientifically speaking, conventional heat transfer from the heated air into the beans directly means that we have less inertia of the mass and much faster response time to profile changes if we want.
If you compare the RFB roasting technique with other hot air roasting techniques, where do you see the differences and maybe the advantages?
Yeah. The coffee beans are moved by the hot air flow only, so the heat input over the entire batch and even into each individual bean is very homogeneous. Each bean gets the same amount of thermal energy, and even more, there are no mechanical moving elements inside the NEOROAST or RFB roasters that can stresses the bean while roasting and wear out over the time. The product temperature sensors are directly located in the bean bed, which means that we have a very high accuracy in measuring and so controlling the product temperature, which means we have a good control over our roasting profile. Few components in the roaster lead to low thermal inertia of the system, which gives us maximum flexibility in the fast changing temperatures in both directions, even during the ongoing roast.
If we now take a look in particular at the curves, what possibilities gives us the NEOROAST which we are denied with the drum roaster?
Let's switch to the roasting curves. This is a classical roasting curve where we can see the product temperature over time inside the roaster. With the drum roaster we can accelerate the heating curve depending on the burner capacity. In addition, the drum will not be able to absorb the energy supplied via the burner quickly enough because the steel cannot be heated up fast enough. On the other hand, the heating path once taken cannot be spontaneously changed towards the running process, since the energy once stored in the drum, so in the metal of the drum, cannot be taken out of the system fast enough. In contrast, we see here a selection of roasting curves that can be run on the NEOROAST or on any RFB roaster, where the energy is provided more quickly via the air as a direct energy stream. This means, for example, that the drying phase can be run much faster, up to 150 degrees bean temperature, and then the speed can be taken out of the complete system while we have time for the Maillard reaction, giving the flavor development the desired time. Likewise, The temperature increase can be started slowly. The temperature gradient, rate of rise, called rate of rise often, can be tightened significantly downwards to the end.
You just mentioned the reduced drying period at the hot air roasting. So from my understanding, this is more or less a wasted time for the roasting master, isn't it?
Yeah, that's correct. And it's precisely in this temperature phase that the hot air roaster is more efficient, since the moisture of the beans is virtually carried along with the airstream, whereas with the drum roaster, the evaporation effect takes longer time. Therefore, with the drum roaster, it takes much longer time to get to the exciting point where the actual roasting reaction and therefore the flavor development takes place.
If we now take another critical look at the greater possibilities of the NEOROAST, is there a curve where you would say you can create an exciting flavor and this is definitely not possible with the drum roast?
Oh yes, we can run profiles with a rather extreme. So for example, this one here, where we have a short drying time and a short drying phase and a prolonged phase in the Maillard reaction time, which means that we have a low increase of bean temperature, so that means we have a low rate of rise. We have a longer time to develop our coffee flavor, which means a high body, high sweetness and juicy acidity and so on. On the other extreme, which we can see here, we could try to have a quite short phase in the Maillard reaction and a prolonged time in the last development phase, which will result in a quite dark brown color with caramelization and low sweetness or even stronger tart and bitter flavor development. This will be in an espresso or coffee served with milk, for example.
Yeah, Stefan, thank you for this good exchange of information, which really inspires us to roast coffee. And yeah, I hope you enjoyed it as I did and you take some inspiration for your roastery. And yeah, if you have any question, do not hesitate to contact us at Mayos Neotech by phone or by email. And I would say, yeah, see you again for a good cup of coffee.
Okay.
Bye-bye.
Bye-bye.